final video for the 3-2 section is brought to you by the sea serpent that the Vikings have to fight when they're on their Viking ship, and it's a big one. Look at it. Look at that one. I got to build this one. It's the Viking little ship. I encourage you to purchase it if you're interested. Okay, so we're going to finish up this section with the effective interest rate. And when we are getting interest rates that are compounded more often than once per year, sometimes it's helpful to know, to compare them, to be able to tell which one, to compare them directly, and you can't. So we define a little thing called the effective rate. We also call that the annual yield. And our author says it's the simple interest rate that would yield the same future value over a 1 year as the given compound interest rate. Well, I agree with this, but it's also the same as a compounded annually interest rate. Recall that compounded annually and simple interest earn the same amount of interest in a 1 year period. Like they're the same, they're the exact same thing. It's only into the second year that there's any difference, because that's when the annual is earning, or the compound is earning interest on the interest. So you can think about these as the same thing for this first year. The compound interest rate that you're handed, we sometimes call the nominal rate. Just be aware of that. So this is the formula that relates the two. Notice that there is no principal in this. Like, we don't need an investment amount. We can just take the interest rate and the number of compounds per year, and this converts it to a compounded annually or simple interest rate. So converts to compounded annually or / simple interest. And that's an equivalent for a 1 year period. So let's say we're given a nominal interest rate of 4%, compounded weekly. What would we expect the effective interest rate to be, higher or lower than 4%? Well, note what we're being told here is that this interest rate is 4, and it's compounded 52 times per year. So because it's compounded more often, like we're depositing the amounts of interest into the account 52 times over the course of the year, it's going to be a little bit higher than just a 4% compounded annually, because we're earning a little bit of interest on a little bit of interest before the end of the year. So let's calculate what the exact, or what the effective interest rate is. And since I've already labeled the things above, it goes pretty quickly. We just take the 0.04, divide it by the 52, raise it to the 52th power, and then we subtract from that 1. This is a great case for Desmos. So notice this is essentially the factor from the exponential deal. Oops, let me raise it to the 52nd power. Hang on, there we go. So this would be the factor in a exponential model. When we subtract 1 from it, we get the rate. So that's why you're subtracting 1 from these problems. And then if we wanted to convert it to a percentage, we'd multiply it by 100, and you can see it's approximately 4.8%. Just as we expected, it would be a little bit higher, about 4.08% interest over a 1 year period. So we're going to find the future value then if we had $10,000 compounded weekly. Well, note that now we're given a principal of $10,000. It's the same R, it's the same N, and our future value formula is the principal times 1 plus the rate divided by the compounds raised to the N times T. Oh, note, I forgot to label that we're doing this for 1 year. Okay, plug and chug, here we go. Again, this is a Desmos sort of situation. Let's make that 10,000, of course. 1 plus 0.04 divided by 52 raised to the 52nd power. Notice, by the way, I could have taken that effective interest rate that we calculated above and just multiplied the two together, and I'd get the exact same thing. We said it was approximately 4.08%. Oh, come on now. So if I put a 1 in there, I'm getting approximately the same values between these two. Okay, so our future value on that $10,000 investment is $10,407.95. Had we just used the 4.08%, we would have looked at that being $10,408. We would have been rounding this 95 to a dollar. Okay, we're supposed to divide our answer in question 10 by 10,000. Ooh, we know what that's doing. We're finding the factor. I don't even need to do this in Desmos. I know it's going to come out to 4.0795. I'm sorry, 0.04795. What do we notice? This is the growth factor. All right, so here's really where this effective interest rate is supposed to come into play, is that we can compare these two interest rates that are compounded at different compounds using the effective interest rate instead of doing a future value calculation. We could, of course, just do a future value calculation, keeping the amount we're investing the same between the two. Or we could use the effective interest rate formula. Either way is fine. So here's my 6.2% compounded daily. Notice that's 365 for our N. And my other interest rate is 0.0625 compounded semi-annually. This means twice per year. So the effective rate, meaning the equivalent compounded annually or an equivalent simple interest rate for a 1 year period, is 1 plus 0.062 divided by 365, raised to 365 minus 1, and then the equivalent for this one scampering off to Desmos. Oops, I forgot to divide by 2. Not there, though. Okay, so for the compounded daily, we're getting approximately 6.396%. And for the compounded semi-annually, we're getting approximately 6.348%. So which is the better investment? That would be the compounded daily. Daily is better because it's a higher investment rate. If it was which is the better loan, I sometimes assume it goes without saying, but maybe it doesn't. When you are borrowing money, you want the lower interest rate because that's going to cost you less money. So if we were in a borrowing situation, the compounded semi-annually is the better loan terms because it's slightly less.